And we're always going to start that by solving the equation, letting the determinant of a minus lambda I be equal to 0. So the first thing that we need to do is to set up what this a minus lambda I looks like. I'm going to take -2, 12, 1, -1. Here's our A matrix. And when we're subtracting lambda times the I matrix, it's important to note that because this is 2 by 2, I need the 2 by 2 identity matrix. I'm going to go ahead and multiply that lambda in right now. And because lambda times 0 is 0, this matrix just becomes a matrix with lambdas on the diagonal. Same thing happens every time we're doing this. That means that when I take my original matrix A minus my matrix with lambdas on the diagonal, we end up with a matrix that has the primary diagonal subtracted by lambdas. And those off diagonal terms get left alone. So we're looking to set the determinant of this equal to 0. Well, to find the determinant of a 2 by 2 matrix, we're going to do whoosh, minus whoosh. So that's -2 minus lambda times -1 minus lambda minus 1 times 12. And that whole thing is set equal to 0. When we get to this point on any of these problems, we're going to want to multiply stuff out. And then we're hoping that it factors. If it doesn't factor, or if you really hate factoring, you can jump straight to quadratic formula. However you want to solve this quadratic equation, totally fine. When I start distributing things out here, I've got -2 times -1. So it's going to give me a +2. I will have a +2 lambda and a +1 lambda and a positive lambda squared and then -12. Oops, I wrote 10, I said 12, and -12. And that whole thing will be equal to 0. I don't know about you, but for me, my brain just factors better if I have the squared term in front. So I'm going to write this as lambda squared plus 3 lambda minus 10 is equal to 0. Personally, I'm pretty good at factoring, so I'm going to go with factoring in this case. Looking for 2 factors that multiply to be 10. I don't really have a choice. It's got to be 2 and 5. So I'm going to have a lambda with a 2 and a lambda with a 5. And now I just have to figure out which of those needs to be positive to give me a +3 lambda term in the middle. I'm going to need a +5 and a -2 to make that happen. Solving each of these, I'm getting an eigenvalue of +2 and a second eigenvalue of -5. There are 2 different methods for solving this, and what I wrote just now mixed up the 2 methods. I'm resetting. Method 1, we could plug the lambda directly into here. Method 2, and the one that you were shown in class on Wednesday, is to rearrange this so that it looks like a minus lambda I times some x vector is equal to the 0 vector. I'm going to stick with this method because it's the one that you were shown in class. So resetting this a minus lambda I matrix, I didn't actually really need to erase it, but I can get it back really quick. Plugging in the 2, that's a -4, 1, 12, and -3. Great. Now that we're here, I'm going to multiply out the left-hand side. And because we have 2 distinct eigenvalues, we are expecting that when we write this out, the top equation and the bottom equation are the same. Let's make sure it works out that way. I've got -4 times x plus 1 times y. And that's got to be equal to 0. And then our bottom equation would look like 12 times x plus -3 times y. It shouldn't matter which equation we work with because they should be the same. Notice if I take the top equation and I multiply through by -3, it would turn into the second equation. I'm going to choose the one with the smaller numbers. So if I look at the top, that says y is equal to 4x. So any point on this line, y equals 4x, is an eigenvector. And we can choose any point on that line. I'm going to label this as lambda1 and label my corresponding vector as x1. And now we need to pick a number. I'm going to choose to plug in 1 for x, and that would make y equal to 4. Now I get to do the whole thing over again. Well, not the whole thing. This whole thing over again, but plugging in a lambda of -5. So if lambda 2 is equal to -5, and I start here, then that a minus lambda I, I'm plugging in -5 here for lambda. So -2 minus -5, the same as -2 plus 5. So I'm looking at a 3, 1, 12, -1 minus -5, I think ought to be a 4. Again, distributing out here, got 3 times x plus 1 times y. That's got to be equal to 0. And from the bottom row, 12 times x plus 4 times y also needs to be equal to 0. Once again, because we had 2 distinct eigenvalues, we're expecting these 2 equations to work out to be the same, which they do. If I take the top row and I multiply it by 4, it's equal to the bottom row. So I'm going to choose the one with smaller numbers to work with. And if I rearrange that, that says y is equal to -3x. And any point on this line can be my next eigenvector. So I'm going to call my second eigenvector here. I'm going to continue the trend. I'll plug in 1 for x, and that would make y -3. So here's my starting matrix: 4, -2, -3, 9. And we're going to go ahead and find the eigenvalues first so that we can find the eigenvector. Because we end up doing this a lot, I think it's faster to just go ahead and build the matrix that looks like A minus lambda I. So that lambda I matrix has lambdas on the diagonal and zeros on the off diagonal. So when we put that all together, we get 4 minus lambda, -2, -3, 9 minus lambda. And really for the rest of the problem, this is the matrix that we're going to be referring back to. To find the eigenvalues, we need to set the determinant of that A minus lambda I matrix equal to 0. So we're looking for the determinant of this matrix, which is minus. So I need a 4 minus lambda times 9 minus lambda minus -2 times -3. And that whole thing being equal to 0. I'm going to give you 30 seconds to practice the actual algebra of solving this out. It should factor, but you're welcome to use quadratic formula. Cool. I'm going to go ahead and distribute this out. So 4 times 9, I've got 36 minus 4 lambda minus 9 lambda -2 times -3 is a +6, but then we're subtracting it. And if we put all of that together, oh wait, I lost my lambda squared somewhere in there. We'll just put it on the end. Because I know that it factors, I'm going to put my lambda squared in the front. And when I combine my lambda terms, I think that's a -13 lambda. And 36 minus 6 should give me a +30. So to factor this, I'm looking for two numbers that multiply to be 30, that add or subtract to give me -13. So I'm looking at a 3 and a 10. So when I write out those factors, I've got lambda -3 times lambda -10. So I now know that my two eigenvalues are 3 and 10. Does that match what you all got? I got a few yeses, so good. Probably means that I did my algebra right. After we find the eigenvalues, now we can move on to looking for those eigenvectors. Technically, the eigenvectors are coming from thinking about this equation that looks like A times the vector X is equivalent to lambda times the vector X. But practically, what we often do is to move everything to one side of the equation so that I would have AX minus lambda X is equal to 0, factor the X out, and be left with A minus lambda I. You don't have to show these steps. When we're finding the eigenvectors, we can move straight into this bottom formula. So to find those eigenvectors, we can start off with our A minus lambda I matrix, where we're actually plugging in a value of lambda. Let's do this for lambda equals 3. So the A minus I times lambda matrix, once we plug in a lambda of 3, turns into 4 minus 3 and 9 minus 3 is 6. So that matrix times a generic xy vector, we need to be equal to 0. Well, when we multiply that out, I get 1 times x plus -2 times y needs to be equal to 0, and -3 times x plus 6 times y also should be equal to 0. This is just like a quick reality check. If you had two distinct eigenvalues, these two equations should always be the same. And they are, because I can take the top equation and multiply it by -3 to turn it into the bottom equation. I'm going to choose whichever equation has smaller numbers. So if I take that top equation and I rearrange it, that would look like x is equal to 2y. Now I know we usually solve things to make them say y equals, but it doesn't matter because we're just finding any point on this line. So this time, instead of plugging in 1 for x, I'm going to choose to plug in 1 for y. So if I plug in 1 for y, this looks like 2 times 1 is equal to x. So y equals 1, x equals 2. That means that the vector associated with my, or one possible eigenvector associated with my lambda of 3 would be, I'll give these subscripts of 1. It's arbitrary, it just means that's the one I found first. I plugged in 1 for y, I got 2 for x. We're going to repeat that whole thing again, but this time for a lambda of 10. I'm about to erase my eigenvalues, so going once, going twice. Cool, let's get rid of it. So again, I'm going to start at that equation that looks like the matrix A minus lambda I times a generic XY vector is equal to 0, 0. There's my A minus lambda I matrix. So when I plug in my lambda of 10, that's going to turn into 4 minus 10, -2, -3, and 9 minus 10 should give me -1. That whole thing will be multiplied by my generic XY vector to give me the 0 vector. When I distribute this out, I'll have -6 times X plus -2 times Y. And on the bottom row, -3 times X plus -1 times Y. Just like with the other ones, because we had two distinct eigenvalues, we expect these two equations to be identical. And they are, because if I multiply the bottom equation by 2, I get the top equation. Just to be consistent, I always choose the one with the smaller numbers. So that's going to be the second equation this time. And when I move the Y over, I'll have -3x is equal to Y. So this time, I'll go ahead and plug in 1 for X, and that would give me a Y value of -3. So if I give those subscripts of 2, then my second eigenvector here is 1, -3. I'm going to take this matrix A, 4, -2, -3, 9, and I'm going to multiply it by one of these eigenvectors. I'm going to choose the eigenvector 1, -3. I'm going to do the matrix multiplication out on that side, but I already know what the answer should be. I need that answer to be the lambda times the eigenvector, meaning I know that the answer I should get is 10, -30. You don't have to take my word for it. Let's actually multiply this out. If I multiply out the left-hand side, this is a 2 by 2 times a 2 by 1. The inside dimensions match, so we're allowed to do the multiplication, and the outsides tell me that the answer will be a 2 by 1 vector. Well, to get what goes in that 2 by 1 vector, doing my matrix multiplication, this top piece is in row 1, column 1. So I would take row 1 times column 1. I'll have 4 times 1 plus -2 times -3. This bottom piece, it's in row 2, column 1. So I'll take row 2 times column 1. -3 times 1 plus 9 times -3. And when we work out the arithmetic here, -2 times -3, that's a +6 plus 4. Hey, we got our 10. -3 plus, okay, well, -9 times -3, that's -27, plus another -3, that's -30. We win. Now, I know that wasn't really that exciting. We just practiced the matrix multiplication. But what's cool about it is if I take this matrix times this very special vector, I didn't have to do any of this. I already knew what the answer would be. I already knew that the answer was going to be 3 times that very special vector. What this lets me do, I'm going to erase this. This part was boring. We're going to do the fun stuff. What this lets me do is suppose for a second that I didn't really want to know what A times x2 was. I actually wanted to know what A to the 47th power times x2 was equal to. Now, nobody wants to multiply this matrix by itself 47 times. That sounds terrible. But this question, this is pretty sweet. So what I'm going to do here is I'm going to say, okay, well, that a to the 47th, that's a times a times a times a times a, whatever, 47 times. We'll just throw a couple more a's in there, and you know there's 47 of them. And we're multiplying that by x2. But wait, a times x2 is really just 10 times x2. We still have all those other a's. A, over here to this a. That 10, it's just a number. It doesn't matter what order we multiply it in. So I could like shove it out to the front. And then look at that again and go, wait, a times that vector x2 is just 10 times that vector x2, and pop another 10 out to the front. Well, if I keep doing this, we're going to end up doing it exactly 47 times, which means we'll have exactly 47 tens being multiplied out in front. And this becomes conveniently just lambda to the 10th. Sorry, I don't even know what I'm writing there. I really meant 10 to the 47th power times that x2 vector, 1, -3. Or if I wanted to do a to the 12,403rd power for absolutely no reason, times the vector 2, 1. This same thing happens each time. And each time when I pull off one of those a's and I multiply it by my eigenvector, out pops it times 3. So this thing would turn into 3 raised to the 12,403rd power times 2, 1. So if I have this matrix A and I wanted to multiply it by some kind of random vector, I don't know, 5, -1. I don't know how in depth you want me to get on this. Obviously, doing the matrix multiplication here is not too bad. But if I actually wanted to do the same kind of thing that we were doing on the previous problem, and I wanted to take that A matrix to, I don't know, like the 400th or even the 8th power times that vector 5, -1, then doing this multiplication out would be super time consuming. You may have noticed this trend in the 17 series. We often want to talk about the long-term behavior of something. Well, in this context, that long-term behavior is going to lead us to thinking about that matrix being raised to a really big number to be looking at that long-term behavior. So we don't want to do all this multiplication out. We would like to have a faster way to do it. Now, the book presents us with a faster way to do it, and they really are just giving us a formula for how to make it happen. Do you all want to see it in slow motion, or do you just want to see how to use the formula? Some people would like me to just show you how to use the formula. Wait, let me give you a poll. You're much better at answering polls than typing stuff into the chat. So should I just give you the formula? Okay, there's a little bit of a split, but mostly we're at yes. Just get to the formula. So I will talk through the what's happening with the formula, and then we'll just do the formula. So the what is happening with the formula is essentially I can take this vector 5, -1 and write it as a combination of these two eigenvectors. So I chose this specifically so that I could do math in my head. And I think that that vector 5, -1 is equal to 2 times my first vector plus my second vector. Oh, no, yeah. So if we can write this vector as a linear combination of your eigenvectors, then we can do that same cool thing and say that a to the 8th times 5, -1 would be the same as a to the 8th times 2 times 2, 1 plus a to the 8th times 1, -3. Also, you don't need to write this because this does not look like the formula, but it's kind of what's happening in the background with the formula. And then this same thing, I can say that's 2 times, instead of a to the 8th, 3 to the 8th times our vector. And instead of that to the 8th, 10 to the 8th times our vector. This becomes P times D to the T times P inverse times N naught. That's a little gross, but I'll show you what all the pieces mean. The first part is that we can write this matrix A as P, which is the matrix of our eigenvectors, times D, which is the matrix of our eigenvalues, times P inverse. So let's start there, and then we'll work into where we're headed. So our matrix P is always the matrix of our eigenvectors, and it doesn't matter what order we put them in, but we have to keep them in the same order for the P matrix and the D matrix. Here's what I mean. I'm going to take my two eigenvectors, 2, 1, and 1, -3, and stack them next to each other to form a matrix. That is my, sorry, let me line this up better. So A will be equal to P times D times P inverse. So our D matrix is going to be a matrix. It kind of looks like the identity matrix, but on the diagonal, we're going to put our eigenvalues instead of 1. Because I made 2, 1 my first column in the matrix, it means that the eigenvalue that goes with that has to go first. So my 3 would go there. And because 1, -3 was my second column, I need 10 to go right here. It would also be totally fine to swap these two and then write your D matrix as 10, 3. Doesn't matter which order, it just has to stay in the same order for each of them. Now this P inverse matrix, that's literally taking this matrix and finding its inverse. So just as a refresher, we've got a formula for finding the inverse. And to get P inverse, I want 1 over the determinant of P. We swap the diagonals. So that'll look like -3, 2. And the off diagonals, we switch the signs on. So that would be a -1, -1. Now to get that determinant of P, 2 times -3, that's -6, minus 1. So that's a -5. So our determinant of P is -5. and I'm going to go ahead and distribute those pieces in. So I'll have -3 over -5, or 3/5, -1 over -5, or 1/5, -1 over -5. Sorry, I lost them. Yeah, no, that was right. That was right. Okay. 1/5, and 2 over -5, -2/5. Now I claim, oh, question about my -5. It's probably a -7, isn't it? -6 minus 1 is indeed -7. I think I just wanted it to be 5 because it sounded like a nicer number to use. So in the interest of time, you're just going to have to believe me that if we multiplied all that stuff out, we would indeed get that matrix A back. Now, what the heck does that have to do with this equation right here? The other day, we had that cool example. We were talking about dogs. We had our puppies, our juveniles, and our adults. We were able to write this matrix that represented, I don't even remember what all the numbers were, but we had this matrix in, I don't know, 0 to 10. I'm making stuff up. We had this matrix that represented our puppies, juveniles, and adults. We had some stuff in here. And we started with an initial distribution of our puppies, juveniles, and adults. And multiplying by the matrix gave us how many puppies, juveniles, and adults we had the next year. Well, if I wanted to figure out how many puppies, juveniles, and adults I had after 2 years, juveniles and adults, I would take that same matrix that I'm just going to call M and multiply it by the answer we just got. So you might imagine that if I wanted to do this a whole bunch of times, that it might be convenient to have some, I didn't mean to just, it might be convenient. No, I did mean to put, yeah. To have some faster way to multiply this matrix by the vector over and over again. And it turns out that this formula gives us the faster way to multiply that matrix by our initial population over and over and over again. And what happens is the same thing that happened when we did it out by hand for the eigenvectors. Essentially, your eigenvalues just keep repeating, multiplying together over and over and over again. And the notation that we use for that is right here with the d raised to the t. There is like so much in this section. I don't know how I was thought I was gonna get through it in a day.